This is Eric Fielding. I'm a geophysicist at the Jet Propulsion Laboratory in Pasadena, California, operated by the California Institute of Technology. And I'll be talking today about how to use SAR Interferometry to study the effects of earthquakes. And we're going to try to show you a review of the basic physics of SAR interferometry. There's a more extensive version of the theory that we presented last year that you should catch up on if you haven't seen it already. I'll tell you a little bit about what we actually are measuring with the phase that we measure with SAR interferometry. And then I'll do a demonstration explaining how to load in the data and then do the in-SAR processing. These are the prerequisites from last year that would be really helpful for you to better understand some of these concepts. The basics of synthetic aperture radar, the data analysis that Erica presented last year, and then the introduction to SAR interferometry that I presented last year. So I'm going to do a quick review of the theory, but skip over a lot of the parts that, so if you need more information, you'll have to look at the last year version. The key point about SAR interferometry is that we're measuring the phase of the SAR signal. It's not the amplitude that, or the polarization that matters, it's the phase. So that's different from a lot of the other applications of SAR. And what is SAR phase? SAR phase is a measure of the range or the distance between the satellite, which we represented here as this satellite dish. Of course, the satellites look a little bit different than that. And the ground. And one of the things to keep in mind is that it doesn't just bounce off the ground as one thing, but it bounces off a number of things that are within one square or resolution or pixel on the ground. So in fact, these different things that it's bouncing off of actually cause the phase of the signal to be random from one pixel to the next. And there's also a huge number of radar wavelengths, millions from the satellite to the ground. Radar satellite wavelength is on the order of a few centimeters to 25 centimeters, and the distance is hundreds of kilometers. So how do we understand, how do we measure this phase in a useful way? The key thing is interferometry. Interferometry is taking the difference in the phase between two different images. And we do that by taking the phase of one image and the phase of the other image and subtracting them. So if we look at the equations for what the phase is made up of, there's this important constant you'll always see in things to do with radar phase is 4 pi over lambda. That's the lambda being the radar wavelength. And this rho here, rho 1 is the distance from the satellite to the ground in first image. Rho 2 is the distance from the satellite to the ground in the second image. And then you can see that that's multiplied by this 4 pi over lambda. That's the key number that converts distance in meters to a phase, because we're dividing by the wavelength here, which is also in meters. And then there's these other constants. So those other constants include the distance, the distribution of scattering within the pixel, and that's unknown from one pixel to the next. But if the ground stays almost the same between the times that you take the two radar images, when we subtract the phase of image 1 from the phase of image 2, these other constants are canceled out. So that's the way interferometry is able to we can't measure these other constants, but we can subtract them out by taking the difference between these two radar images. There's also some this N here is to represent noise sources, which are also going to be different between image 1 and image 2. And we'll talk about that a little bit later. So just to give you a rough idea of what are the main applications of SAR interferometry, the first application that of SAR interferometry that you may have heard about is that SAR interferometry was used to do the mapping the Earth's topography in the year 2000 on the shuttle radar topography mission, which used the space shuttle and a big radar antenna and a boom to measure the Earth's topography by taking two radar images simultaneously from positions that were 60 meters apart. And that allowed us to measure the topography of the Earth up to plus or minus 60 degrees, which is the limits of the space shuttle orbit. And there's other, I should mention that we recently, JPL released a new version of the reprocessed data from the shuttle radar topography mission. It's now called the NASA DEM. And that was just released in May, I think it was. And that's now available from the DAC, the Archive Center at ARSET Data Center. There's also, radar interferometry is also used by airborne platforms. With an airplane, you can get higher resolution, not surprisingly, because you're closer to the ground. There's a new system that NASA operates that was built by JPL. It's called GLISTEN, and that also uses this single pass interferometry with two antennas to measure the topography of the ground surface. And that's being used to map glaciers and volcanoes and other things that are changing rapidly. One of the key things that when you process the radar interferometry data is that it's automatically in a geocoded coordinate system. A lot of times when people are starting to do these new techniques like shape from motion with drone images, they need some external reference to tie down the DEM, but the radar imaging is automatically geocoded, so that's a big advantage. And it can cover a lot of area in a short period of time compared to a lot of the other methods like LiDAR. It doesn't have quite as high resolution as LiDAR or low altitude drone photography. Of course, down at the bottom here, there's a lot of applications of topography data, land use management, determining where the height of trees, measuring landslides, lava flows, like the huge lava flows occurring now recently in Hawaii, changes in glaciers. The GLISTEN instrument was originally developed to measure the glaciers in Greenland, and it's been collecting data there for a couple of years, especially under the Oceans Melting Greenland project. The other big application of SAR interferometry is measuring deformation. And that's what we're going to be concentrating on today, which is measuring the deformation due to earthquakes. So the big difference here is that we're taking two radar images at two different times and then subtracting those. And that tells us about the amount of deformation that's happened between those the times that those two radar images were acquired. The topography data is best acquired by using two antennas acquiring data at the same time, so that there's no change in the ground surface. But for deformation mapping, we want to have a time difference so we can measure the deformation that happened during that time interval, such as an earthquake. The big advantage of SAR interferometry is we can measure between 1/10 of a centimeter and a centimeter of displacement, depending on the radar wavelength. We can get the spacings as small as 10 meters or even a little bit smaller with certain techniques. Other satellite systems use a resolution that's closer to 100 meters. And the area that we can measure varies from about 10 kilometers wide to 350 kilometers wide for the widest INSAR digital displacement model maps. And of course, as we're talking about today, one of the big applications is earthquakes, but it can also be used for measuring deformation due to volcanoes. Volcanoes have large amounts of deformation, landslide motion, subsidence due to groundwater withdrawal or extraction of gas or coal or other materials from below the surface. The motion of ice sheets, glaciers, and large ice sheets. And it can also be used to measure the heights of trees in certain cases. And also for disaster monitoring, we can do estimates of where the ground surface has changed by the difference in how the radar is reflecting. The phase can be changed a lot by things like destroyed buildings. So that's a useful method for application for SAR interferometry. So just to show you a little bit more about how the what we call differential interferometry works. We call it differential interferometry because it's subtracting out the topographic signal. If we had the two images, if we were able to get the satellite back to exactly the same location at the second time, then there would be the phase difference here, delta phase, would be exactly equal to the change in range between the ground location of reflectors at the two times. And then we can use that same 4 pi over lambda factor to convert it back to actual distance change, rho here in meters. So the key thing to remember is that for the differential interferometry, where we're trying to measure, where we've subtracted out the topographic signal, is much more sensitive than the sensitivity to elevation. We can measure on the order of a few millimeters of surface deformation, whereas with the topographic sensitivity, we can only measure meters or even tens of meters. The errors in the shuttle radar topography mission data are up to 10 meters in place in much of the world, so because of the less sensitivity to topography than what we have for measuring surface change. So these are just writing out those sensitivities in equation form. At the top here, we can see the sensitivity to topography depends on this B. That's a B perpendicular, the perpendicular baseline between the two radar antennas. but it's also divided by the range down here, because the range is hundreds of kilometers. That greatly reduces the sensitivity to topography, whereas the sensitivity to the displacement, as I mentioned, keep saying, is this 4 pi over lambda factor, where lambda is the radar wavelength. And these are just the derivative forms. So the next key thing that we need to consider is something called phase unwrapping. When we measure the phase of a signal, we measure it modulo 2 pi. You can only measure the phase relative as it goes. It wraps around when we're measuring it. It's like a circle. So if we have here the actual phase being a ramp and this like a linear trend, when we measure it as the interferometric phase, it gets converted to a wrapped phase that only goes between minus pi and plus pi. And what you really want to understand is what the original phase is. So we have to do this unwrapping step, which we'll talk about later. But one of the other things to notice is that when we unwrap the phase, it can be, whereas this previous, the original phase started at pi and started at minus pi here. When we unwrapped it, it might come out with some other shift here, because we don't have the absolute phase. It's always relative to some unknown constant. That's a key thing to keep in mind, that there's always this unknown constant here, plus phi constant that you don't know, and have to try to figure out with some other information. The other thing about the interferometry is that it has what we call the coherence or correlation. Coherence is often used to describe the how coherent well defined the signal is, but the way we measure it is actually using a spatial correlation. So you'll see both terms used. Some people call it coherence, some people call it correlation. In the SNAP software, they call it coherence, but a lot of people call it correlation. So you just have to understand that both are really the same thing. And there's a lot of things that can cause what we call decorrelation or loss of correlation or becoming incoherent. If there's a lot of noise in the radar data for some reason, if the ground surface geometry or volumetric scattering changes, if the viewing geometry is rotated for some reason, like the ground surface rotated, or if there's just random motion between the two times that the radar images are acquired. And what we do is basically measure the local, the correlation of the phase over some local area. Typically, it's about 5 by 5 pixels. And that's how we estimate the coherence. And that coherence is what actually is the one way to measure how accurate your measurements are. And it'll affect the accuracy of how you can measure displacement of the ground surface or height. And it also, if the coherence is too low, it affects your ability to unwrap the phase, because the noise can make it impossible for the computer to figure out what the correct phase is. Unlike phase, which includes different components that are added together, the correlation effects are multiplied together. So if we have, we usually use this symbol, Greek symbol gamma, to measure the measurement of correlation. And so the total gamma here is the multiplication of the volumetric correlation and the geometric correlation due to the slopes or a large baseline, the temporal decorrelation, and any kind of sudden change, like due to earthquake destroying buildings. So, and this is also going to depend on the radar wavelength. So one of the things to remember is that different radar wavelengths are bouncing off of different things on the surface. So the radar interacts most strongly with the objects that are around the size of the wavelength. So if you're looking at a L band, which is a 24 centimeter radar wavelength, it's going to be bouncing off things like the tree trunks and the ground surface. So it's not going to see the leaves on the trees unless they're banana leaves or something very large. The C band, which is one of the most common bands used by satellites these days, is 6 centimeter wavelength. So that's going to be bouncing off things that are like branches in the trees and sometimes, to some extent, the leaves. And then the other common wavelength is the X band, which is 3 centimeter wavelength. And that, because it's even shorter, is typically bouncing off the tops of the trees and the leaves of the trees and other plants on the surface. So it's going to be more sensitive to motion of smaller objects, and which can be a problem in heavily vegetated areas for making deformation measurements. Same kind of thing happens with dry soil in desert areas. In some cases, the L-band radar can go as much as a meter into very dry sand, whereas the X-band is going to be bouncing off layers very close to the surface. And similarly with ice, the shorter the wavelength, the closer to the surface the radar is going to be reflecting. In fact, it's not shown on this slide, but there's another band called Ka band, which is 1.5 centimeter wavelength, and that's what's used for the GLSEN ice topography mapping mission. And it's also important to remember that because the different wavelengths are reflecting off of different things, this also affects the ability to measure the INSAR phase. So here's an example. During the shuttle imaging radar or mission C, or SAR-C mission, which flew in 1994, they flew the space shuttle twice in 1994, 6 months apart. And that radar, that in fact had 3 different kinds of radar on it. We're showing 2 of them here, the C-band measurements and the L-band measurements, which were made at exactly the same time with the exact same geometry. And we can see here on the left that the C-band radar has a very low coherence or high noise level in the areas of, this is part of the Big Island of Hawaii. There's these dark areas here where the radar, the C-band radar is bouncing off the trees. These are the heavily forested areas of the Big Island. And these bright areas with good coherence are the areas with it where it's bare lava due to fairly recent lava flows. Whereas on the right here, we can see that at L band, the 24 centimeter wavelength, the fringes go right across, even in the vegetated areas, and we're able to measure the interferometric phase everywhere because it's less affected by the vegetation. Over here on the right, there's these three plots showing these are measurements of the correlation. Correlation, it goes from 0 to 1. That's our measurement of coherence. So low correlation is these blue colors, high correlation is these yellow colors. And again, we can see that the C band has low correlation in the vegetated areas. L band has considerably higher correlation. And just to compare it to, we took a normalized difference vegetation index over here, NDVI, and used the same color scheme to compare it to the radar. You can see that there's a very high correlation between the amount of vegetation and the level of coherence. So that really shows you how it depends on the radar wavelength. So here's some more examples of INSAR applications, just showing some pretty pictures to get you started on some ideas. We can measure earthquakes. This is one of the classic earthquakes called the Hector Mine earthquake up here at on the left. That happened in 1999 in Southern California, out in the Mojave Desert. Very excellent interferogram with a C-band radar from the ERS satellite. It's in the desert, so there's no low correlation because it's all there's no vegetation. In the middle here, we have an example. This was done by one of my colleagues, Jill Peltzer at JPL. He used ERS C-band radar to measure subsidence in the area of Pomona, east of Los Angeles. And due to withdrawal of groundwater, the ground surface is going downward over the course of a 2-year time interval here by about 15 centimeters in the middle of, in the area of highest subsidence. There's over here to the right, there's a map of ice velocity. This is measured by a combination of SAR Interferometry and what we call pixel offset tracking, which is another technique that to measure very large motions, which I won't be covering today. And then up here on the right are some pictures from a whole series of measurements of the Mount Etna volcano that were made at different times and then put into a movie, which you find online. Then there's also things like this dike injection that happened in Ethiopia in what they call the Asal Rift. This happened in 2005. This is an MBSAT interferogram with a relatively short interval from May to October. This red line here shows the location of where the dike was injected, and this field photo shows how, as the dike intruded into the upper part of the crust, it pushed the sides apart and caused a big collapse. There was a similar dike injection in Hawaii just in May of this year on the what they call the lower east rift zone of Kilauea. And in that case, the ground surface was pushed apart by about 4 meters that we measured from SAR Interferometry. But it didn't, in that case, there was so much magma coming in that it is now forming a new magma. A huge amount of lava extrusion is continuing from that area, it didn't open up a big hole in the ground at the surface. It's just been filled in with magma, and so much new magma is moving into that part of building new land, and destroyed a lot of houses, unfortunately. I think it's up to over 500 houses. This is an example of an earthquake that happened in Nepal in 2015. It was a magnitude 7.8 earthquake. And this is an interferogram from a Japanese satellite called ALOS-2. And it has a very wide radar swath, 350 kilometers wide. So we're able to measure the deformation of the whole length of the earthquake. The earthquake rupture is about 180 kilometers length. And we can see that the area around Kathmandu was pushed upward in red colors, and the area to the north in the high Himalayas actually was dropped down, which is interesting and something we're continuing to study. Just for comparison, we also measured this deformation with GPS stations. These little black arrows are showing the motion that was measured by GPS. This was published in that paper from there. This is an example of creep on the San Andreas Fault in California. The two sides, the central part of the San Andreas Fault moves continuously. It has no major earthquakes that we know about, but it moves gradually all the time. So the SAR Interferometry is able to measure that the ground surface has been displaced. In fact, it's moving it up to 20 millimeters a year, every year. You can go to this town of San Juan Bautista and see the places where the fault is pulled apart sidewalks and curbs and buildings due to this ongoing creep. But with the INSAR, we can actually measure it over a large area. As I mentioned earlier, we can also look at the coherence change or decorrelation. This is a interferogram that I made in 2004, just after a large earthquake that happened in southeastern Iran. It was called a magnitude 6.5 earthquake near the city of Bam. And there was a extremely high damage to the city, which is very unfortunate. At least a quarter or maybe a third of the population was killed by the earthquake. And it was a substantial number of people. So it was important to try to understand what happened with this earthquake. And one of the things we noticed right away was that there was this line of low coherence that was extending southward out of the city. And these black circles show. We sent this image to our colleagues in Iran that worked for the Geological Survey there, and they went out to the field and they found that there were surface ruptures right out at these locations of the circle. So they were able to confirm that the coherence change here was due to the surface rupture of the earthquake. And on the way to make that even more obvious is to take the difference in the correlation between a pair of images before the earthquake and another one after the earthquake, and that shows the change here as a red, meaning that the correlation decreased, and that shows you the surface ruptures extending south of the city very clearly, and it also shows the large amount of red in the city of Bam, which is unfortunately due to the destruction of buildings, a lot of which had people in them that were killed. So it was it's now been turned into what we call a method for making damage proxy maps for how estimating how damaged cities are after earthquakes using radar interferometry images. That's just showing where the fault rupture was. And unfortunately, it ruptured towards the city of Bam, and that made the damage in the city worse. Another thing that we can measure is motion of landslides. This is using the airborne radar system called UAV SAR that NASA operates. We took radar images from 4 different directions, did the interferometry, and then combined the 4 different directions into a full 3-dimensional map of the landslide motion, which is really helpful for better understanding how the landslide is moving. The landslide in Colorado that moves up to 2 centimeters every day, a very unusual one. I wanted to tell you about the different satellites that are available in general. Some data is more available than others. The European Space Agency operated 2 satellites, ERS-1 and ERS-2, starting in 1992 and running until 2001 in good shape. The ERS-2 satellite continued to operate until 2011, but after 2001, it was in a degraded state that they couldn't control the satellite as well as they liked, and it's not always useful for interferometry. There was a Canadian Space Agency satellite called RadarSat-1 that was operated from 1995 to 2013. That one also is a C-band satellite. RadarSat-1 had a 24-day repeat cycle, but RadarSat-2 is a little bit shorter than the ERS-1 and ERS-2, which both had 35-day repeats, except for a short time when ERS-1 satellite was moved to different repeat times. There's the European Space Agency NBSat satellite that was operated from 2003 to September 2010, then moved to a different orbit. The original orbit was 35 days, the same as ERS-1 and ERS-2, but after September 2010, they moved it to a different orbit that had a 30-day repeat and was drifting, so it was less useful for interferometry. And that was also a C-band satellite, 6-centimeter wavelength. The Japanese Aerospace Exploration Agency, JAXA, operated a satellite called ALOS from January 2006 to April 2011. That had a 46-day repeat, quite a long time repeat interval, and it that one was an L-band satellite with a 24-centimeter wavelength. That data is largely available over the Americas. The ALOS data is of almost all of the Americas is available from the NASA Alaska Satellite Facility, and over Europe and Africa, it's available from the European Space Agency. In other parts of the world, it's somewhat less available because JAXA hasn't been able to put it online. There's 2 X-band satellites operated by the German Aerospace Agency, DLR. TerraSAR X was launched in 2007. And then a second satellite called Tandem X was launched in 2010. Those 2 satellites are still operated in orbits very close to each other. So they're able to do that single pass interferometry to measure topography that's similar to what was done with SRTM. And they, over the course of about 4 years, collected enough data to make a global digital elevation model, which was done with a commercial partner, so it's largely available only as a commercial DEM product. But they did provide some data to some limited areas to scientists. The Italian Space Agency operates a set of 4 satellites called Cosmos SkyMed constellation. They were launched between 2007 and 2010. Each satellite has a 16-day repeat, but because there's 4 satellites, the repeat interval can be as short as 1 day between 2 of the satellites, so 4 days between 2 of the other satellites, and then 8 days between the other satellites. And again, this is X-band, so it's a 3-centimeter radar wavelength, and it has the higher rate of decorrelation in these areas. Canadian Space Agency also operates a satellite called RadarSat-2. It's still in operation. It was launched in 2007. And that has the same 24-day repeat as RadarSat-1 and C-band radar wavelength. Next year, the Canadian Space Agency is planning to launch a RadarSat constellation mission, which would be 3 satellites. The newer spacecraft that have been launched recently are the European Copernicus Sentinel-1 satellites they're launched by the European Space Agency, but they're actually owned by the Copernicus organization that's funded by the European Union. It doesn't really they care about that in some places, so it's important to point out that it's owned by the Copernicus organization. They have launched 2 satellites. Each one of the satellites has a 12-day repeat, but they're launched in such a way that there's a 6-day time interval between the 2. And we'll be looking at some Sentinel-1 data a little bit later in the demonstration. And all of that data is available for free from the European Space Agency Science Hub. The JAXA, Japanese Space Agency, launched another satellite called ALOS-2 in 2014. That has a 14-day repeat cycle, and it's another L-band satellite, so it has a 24-centimeter radar wavelength. The Indian Space Agency launched a satellite called ARSET-1 that has a 25-day repeat, and that's another C-band satellite. And finally, we're busy at JPL building a new radar to be launched on a joint mission with the Indian Space Research Organization that's called the NISAR mission, and that's planned for launch in late 2021. That will have a 12-day repeat, and it'll again be an L-band radar. This is a little bit more information about the NISAR mission. It'll have a high spatial resolution by using a special technique we call sweep SAR, which I don't have time to explain, but it gives us a wide swath and high resolution. It'll have a second radar in addition to the L-band radar. It's called S-band. It's a 12-centimeter radar wavelength that's being built by ISRO, the Indian Space Research Organization. And that's at present, that's mostly going to be acquired over the Indian subcontinent. It may be acquired in other parts of the world. The L-band data will be acquired over the entire Earth every 12 days. And it's going to be operated to be fully interferometric all the time by controlling the orbit. And all the data will be free and open as the standard NASA policy. So how do we actually do something with the radar data? The first thing we want to do is actually get some data. One of the key types of data nowadays is that's freely available is the Sentinel-1 data. There is you can get the Sentinel-1 data from the European Space Agency website, Sci-Hub, or you can also get it from the NASA Alaska Satellite Facility. I usually get it from the Alaska Satellite Facility if it's here in North America, and we get it faster from there. But there can be a delay of a few days between the time that the data is acquired and the time that it's copied over to the Alaska Satellite Facility. So if you want to get the most recent data, you need to get it from the European Space Agency. This is just a picture of their web page about INSAR. They have a lot of information about their different products. And in addition, they have some of these special, what they call beta getting products. This is part of the getting ready for NISAR that we'll be talking about later. As NASA is getting ready to process data from the NISAR mission, we're using some Sentinel-1 data to prototype the interferometric products that we're going to be producing from NISAR. So there's some of these interferogram products available for certain areas, and I'll be showing one of those later. So today I'm going to be talking about doing a demonstration of interferogram for an earthquake that happened in Mexico in February of this year, 2018, 16th of February. There's actually been a number of earthquakes in the last, since September of 2017. There were, in September, there were these other 3 earthquakes, an 8.2, a 7.1, and a 6.1. And then in February of 2018, there was a 7.2 near the city called Pinotepa Nacional in Oaxaca, Mexico. And that's what I'll be talking about today. So what we can do is go to the Vertex search tool at the Alaska Satellite Facility and search for the data. Okay, so as we go to the Vertex search tool at the Alaska Satellite Facility, this is the search tool that that comes up. You can choose whether you want to search by geographic area, whether you know the actual granule that you want to find, or get all the data from a certain mission. We're going to do a geographic search, and we're going to actually enter in the coordinates of the area that we want to cover. And the area we want to cover is the area that's written here on the slide. Minus 99. So this is the area of the Pinotepa earthquake. We don't want to do a seasonal search. It automatically selects Sentinel-1A and Sentinel-1B. That's as default. And oh, but let's go back. We do want to get data from a certain time interval. We want to go from 2018 to 05. 02 to 2018 02 17. I just happen to know those are that includes the time of the earthquake. And I also know that I want to get data from track number 5 of the Sentinel satellite. So it tells me that there was one pair of scenes here. So we want to get this box includes actually 2 frames of the data. We just get the one that's the frame to the south. It covers the earthquake was close to the coast. And what you want to download is the single look complex image from the 2 different dates. Those are the 2 different granules here. As explained in the, so each one of these is 4.75 gigabytes. It'll take a while to download, so I'm not going to download that now. I'll show you in a minute what we're going to do next. So that's one of the dates. This is the the February 5th image before the earthquake. This other one is the February 17th image after the earthquake. These are 12 days apart, and I can see that these were both acquired by the Sentinel-1B satellite and on 2 successive orbits of that satellite. So that's how we get the data. In order to do interferometry, you have to make sure you get the SLC single look complex data products. Those are very large, but that's what we need to use for interferometry. So now let's go back to the slides. This is just explaining the same thing I just said about which one we want to download. So the next thing we're going to do is go to using the Sentinel-1 toolbox. This is the same toolbox that we used for previous demonstrations for the other amplitude analysis. So you start it by however you start it, clicking on the desktop. And so then you go to open product, and then you can open the SLC image. So let's go ahead and start doing that. We'll start the that image that's shown on the screen at the moment is the final product at the end of this. One of the things that the Sentinel-1 satellite uses the mode called TOPS, terrain observation by progressive scans. That means that it's 3 different subswaths. Those are labeled IW1, IW2, and IW3. This particular product was collected with 2 different polarizations, VH and VV. We can look at both of those. They look somewhat different. Some of the other exercises you went into how to use that difference between different polarizations to better understand what the surface is. But for the purposes of interferometry, we only need 1 polarization. So generally, the signal coherence is better in the VV polarization. So we're going to only use the VV polarization from now on. So you can open. This is the This is the SLC image from the first product. The second image, open product. Well, I've already opened this before, so I'm just going to go down here and reopen it. This is the second image. These other ones are open also. Again, we can look at the subswath 1 VV, and it looks very similar. Not surprisingly, because it's the same area, the same polarization. And in fact, if it changed drastically, it probably would be incoherent. Okay. Go back to the slides, review here. This is just explaining how the SLC data has a different format than the GRDH products that were used in the other demonstrations. The GRDH products are already converted to ground range, and so the subswaths and the bursts have been merged. You don't need to worry about those, but with interferometry, we're looking at the single look complex images, which are separated in the subswaths, and they, if we look closely, we can if we zoom in on this image, you can see there's these black lines here, and that's where, because the radar is actually switching back and forth between those three subswaths. It illuminates one in a burst of radar echoes, then it illuminates one of the other ones, and then it illuminates the other one of the third one. So in these gaps here, it is where it's illuminating the other part of the ground surface. That's just one of the disadvantages of this particular mode that they use for getting the wide swath of Sentinel 1. The SLC product has these 4 different categories: the metadata, the tie point grids. It could have vector data. It doesn't come with any. Quick looks. There is a quick look of the whole scene that includes actually the information from both the polarizations. So you can see some colors due to the different response to the ground surface, VH and VV. And then what I viewed is down here under bands, which was the intensity band from intensity of band IW1, VV. So that's explained in this. Oh, and then we can also, this slide, we can also look at this, what they call the world view, which shows the location of the image on the Earth. And you can zoom in and see the details. And this will show that, in fact, what I'm displaying here is the subswath that's on the west side. It's subswath 1, this is an ascending track, and the subswath 1 is to the west. So the next thing is now that we've opened the 2 interferogram, the 2 SLC products, is to start the INSAR processing. And so the first step is to co-register the 2 scenes. We have to, the key thing to do interferometry is that the 2 scenes have to be precisely co-registered. So the first step of doing any kind of interferometry is to make sure the 2 scenes are precisely co-registered. The Sentinel-1 A and B satellites work together. They're in the same orbit. They are designed to be compatible. And they have excellent orbit information. So we can do the co-registration purely from the information that comes with the data, including the precise orbits. So the first thing we need to do is to do the co-registration. We go back here. Okay, so we have the two SLC images opened here now, the one from February 5th and the one from February 17th. The next step is to do the co-registration. So we go to radar co-registration. We have to use the special TOPS co-registration. Sentinel 1 TOPS co-registration. Let me open this window a little bit bigger. It's explained in the slides here also. You have to choose the product for the first date. This is going to be the master date and the reference date in the in the interferogram, and the read number 2 is the second scene or the co-registered scene. We need to make sure that's set to the second date, the 17th. And then for each scene, we have to tell it which subswath. We want subswath IW1 and polarization VV for the first scene. And for the second scene, same thing, subswath 1, polarization VV. It's going to go out and get the precise orbits. We're more than 21 days after the Earth after the acquisitions, so it has precise orbits available. It'll automatically go out and get the data. Under back geocoding, it shows that it's going to use the SRTM 3 arcsecond DEM. It'll automatically go out and download that to do the back geocoding. It's part of the precise co-registration. And then here under write, we choose where we're going to write out the data products. You can choose a directory here. I've set up this directory process data products under a demo project here. And you can see that the output name here is then the name of the first master scene, reference scene with orb stack added to it, the end of the file name. So I'm not going to press run right now because this can take quite a few minutes to run. And I'll skip ahead to show you what the outputs are because I've saved those in this project. So because I've saved the output here, I have it already saved in the project. I'm just going to move this over. Well, anyway, the orb stack product here. Oh, I double clicked it, so it's already opened. So this is what we would get if when we run the co-registration, get a new image. We look at the bands, and now you can see it has the complex images are made up of the what radar engineers call I and Q. I'm not sure where they get that I and Q from, but that's the real and imaginary part of the complex numbers, and it's from subswath 1, VV polarization. This is the scene from the February 5th, 5 February scene. And the second one set is for the scene for the 17 February scene. There's the intensity images again. They look very similar to what we had before, but they're now precisely co-registered. So the next step go back to the slides, is forming the raw interferogram. So once the scenes are co-registered, then we can make an interferogram. We go to radar interferometric products interferogram formation. It automatically selects the last product that I had open, which was the orb stack product. That's the stack of the two scenes. It's called a stack because you can actually do multiple scenes and they'll all be co-registered. In this case, the stack has only two scenes. You can see again, the system automatically added something to the name. In this case, it added IFG it's short for interferogram, to the file name. The processing parameters don't usually need to be changed. This process is pretty quick. I'm going to just run that. First, it writes out the empty file. Then it goes through and does because these scenes are already exactly co-registered, all it's doing is going through and taking the phase difference, and it does that by actually multiplying by the complex conjugate, which is just a standard way of subtracting complex numbers. Again, this can take a few minutes to run. While it's running, I'll go back to the slides. So as I was just saying, by default, it adds IFG to the name, and we don't need to change the processing parameters. So in a few minutes, we'll be able to go through and see the results. Okay, well, I'll just show the final result here. IFG product that I saved in this project. Again, you can look at the bands. Now, because we've taken the difference between these two radar images, we have both the intensity and we have a new phase band. So we can look at the phase band. And it takes a little bit of time to load. This is going to be the wrapped phase. We haven't done any phase unwrapping yet. So the phase goes from positive pi to minus pi, or minus pi to positive pi, depending on which way you look at it. I have the color manipulation window open over here. You could see the range. It finds the minimum is minus pi and the maximum is pi. Making a rainbow color scheme for that interval. So this is the phase. It's minimum. It's wrapped, so it's minus pi to pi for the phase values. We can also look at the coherence image. And coherence goes from roughly 0 to very close to 1. That's showing the coherence. Bright areas are higher coherence, lower areas are lower coherence. Some of these dark areas are heavily forested here on the coast of Oaxaca, or in the mountains. Go back to the phase image. If we zoom in on the phase image, you can see that there's still these boundaries between the bursts. So the next step is actually to do what we call debursting, which gets rid of those discontinuities between the bursts. So as you can see on the slide, you had to go in here under the special Sentinel 1 tops mode, tops deburst. The product is it's the IFG product, the interferogram. And the output, again, it adds another suffix to the name. In this case, is DEB for deburst. There's no processing parameters to choose. I won't run this time. I'll just let it, I'll show you the result, which I have saved in my project. I want the deburst version. Again, the bands look the same, but there's no longer those discontinuities between bursts. You can also see there's a slight overlap between the bursts before I did the debursting. That's just the way they operate it. The debursting process gets rid of those repeated areas. Now this interferogram is still the original interferogram. It still has some topographic phase. This particular pair has a very short baseline, so it's very insensitive to the topography. But we still need to subtract out the topography to make a differential interferogram. So the next step is interferometric products. Interferometric products, topographic phase removal. Again, it automatically selects the source product to be the last product that we just generated, and it's going to add a new suffix DINSAR for differential INSAR. In this case, it's going to automatically use the SRTM 3-arc-second data to do the topographic subtraction. I'm not going to run this again to save some time. We'll skip ahead and go back to the saved products. My DINSAR product here, which processed earlier. And we display the phase here. It's still wrapped phase, but now it has the topographic component subtracted. As I was saying, this particular pair has a very short baseline, so the phase doesn't really look that much different after subtracting the topographic phase. Sometimes the snap display doesn't show the whole scene. It's just a display issue. I don't know what. You zoom out a little bit, usually it fills that in. But if we zoom in, we can see this is the debursted and topographically corrected phase. And you can see these fringes here, this area up here at the top with all the bullseye pattern, that's the signal from the earthquake. But it's still very noisy. So we want to improve the quality of the interferogram. One of the ways to remove noise is to do filtering. So there's a special interferometric filter called under interferometric filtering Goldstein phase filtering, named after Dick Goldstein. They wrote a power spectrum filter. It's published in Goldstein and Warner. It was 2000. 2001, something like that. Again, the input is the last product that we add, and the output is the same, is adding a FLT for filtered. You can change this filter exponent, but generally the default parameters work well. I'm not gonna run this. I'm just gonna go back to the saved product, open the filtered version. If you did press the run button, it will be automatically opened here in Snap. Look at the phase. After this Goldstein or Goldstein-Werner filter it takes a power spectrum in areas. That's the window size that's in that parameter. In this case, the default is 64 by 64 pixel windows, and then it takes the power spectrum and raises it to a power that tends to improve the signals that are coherent and reduce the signals that are incoherent. And it's quite an effective filter. So now we can see that the fringes are much more visible and not as noisy. It also works much better in the places where the coherence is high. You might remember that there was I think this is the area of the city of Pinotepa, Nacional, and then surrounding more populated areas. So the coherence is higher in this area to the left of the main area of fringes. And then the next step that I always do is what we call multi-looking. Radar engineers always use this term called they call it multi-looking. Most other people would call it averaging pixels. We're going to take the original pixels and average multiple pixels in each direction to get a coarser resolution, but a higher quality, lower noise measurement. Because this earthquake is relatively deep, we're not going to lose any information. We can see here that the fringes are pretty far apart. So taking multiple looks won't cause any loss of information. And that's under radar multi-looking. The input again is our filtered interferogram. The output is going to add underscore capital ML for multi-look. Under processing parameters, we have to choose the bands we want to multi-look. And it's very important in this is to multi-look the original I and Q band. I'm going to hold the command button to select multiple things. I'm going to multi-look the intensity, but I'm not going to multi-look the phase, because if you multi-looking the phase will give you a bad result, because this is when you can't multi-look wrapped phase and get any useful results. You have to multi-look the original I and Q components of the complex phase interferogram. You can't multi-look the phase. And I'm also going to multi-look the coherence. This particular scene, I'm going to choose a multi-looking of 17 in range. The default is to make the pixels square in ground range. GR stands for ground range. So it automatically calculates that it's going to take 5 looks, or average 5 pixels in azimuth in the along track direction, and 17 in range, because Sentinel TOPS mode has much higher resolution range than azimuth. And it's going to make the final pixel size about 70 meters on the ground. So I'm going to run this. Takes just a short time, usually. Okay, and this is the result of the multi-look operation. Again, we have well, because I saved this image, normally it would only have the I and Q and coherence after I did the multi-looking. And then you have to go up here under raster image analysis, data conversion. You have to select the I or Q and convert complex I and Q to phase here in order to create the phase band. Also going to convert the I and Q to intensity to make an intensity band. Same thing you have to do for the phase band, which I had done earlier before I saved this. Now we can see that the multi-look product has a different shape. It's because we took more looks in the range direction. It's narrower, and we can see more in the azimuth direction too because it's taken looks in that direction as well. So, and because of the averaging process, we've also reduced the noise rather dramatically. These fringes are much more clear, and this will make it much easier to do the next step, which is the phase unwrapping. This is the main signal from the earthquake. You can remember that this is a C-band radar. That means that we need to divide by 4 pi, or 2 pi is one circle or set of color fringes. So we need, if we take the radar wavelength, 6 centimeters, and divide by 2, and then we get the number of fringes, a number of meters per fringe, because each fringe is 2 pi radians. So each one of these fringes is 2.8 centimeters, and we can count from here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 fringes. Each fringe is 2.8 centimeters. 0.8 times 12. We have about 33 centimeters of displacement here in this earthquake signal. But that process of counting the fringes is exactly what we do in an automated way to get the phase unwrapping. So the next step is to do the phase unwrapping. The SNAP application does not include phase unwrapping, so we have to do export the data and then run an external third-party program. That's explained here in the this is the multi-looking slide. Converting to phase. So we have to use what we call snafu export. They have a special command up here under radar, interferometric, unwrapping, snafu export. Again, it's the last scene, the last image product that we had, which is the unwrapped SAR filtered multi-looked interferogram, and then snafu export. First, I want to set up these other parameters. I want to change the statistical cost mode to smooth. I think that's a better, that works better for most purposes. I'm going to change the number of tiles and rows and columns to 1. Number of processors 1. The rest of these don't need to be changed. Then we have to choose this target folder. I'm going to find my processing this into this Google Drive, Mexico. Demo. Snafu Unwrap. This software has a funny. You can either create the folder in your own terminal, or in this case on the Mac, which I'm using, there's a new folder button here to create the folder. I already created the folder. So in fact, you can't just select the folder. This is a little bit of a kludge in the way that version 6 of Snap works. I have to go in and actually type the name of the folder here instead of pressing the select button. Now the target folder is here. That means it's going to write the output to this folder. Again, I'm not going to press run. I'm going to go to the terminal and do the Snafu unwrapping. This, as I have here in the slides, it's going to write out the phase of the image and the coherence image and what they call a snafu configuration file, snafu.conf, and it's going to write those out to your file system, and you have to go in and run snafu. ESA now provides pre-built binary executables for Windows and Linux. I don't have a Windows machine here to show you, but so I'm not sure exactly how to run it. You can check on the forum. On the Mac, you have to actually compile it. It's actually it's easy. Once you download, you just type make. Then you have to add the snafu bin to your directory, to your path in the shell. There's things online to explain how to do that. And then we have to go through the terminal. Let me get rid of these other ones. There's my snafu UNW directory, cd snafu. And you'll see that it's created a new, under the snafu UNW directory, it's created another directory name that's got the whole name of the product that you exported with the ML at the end. Here's the files. There's a phase interferogram image and header, coherence image and header, snafu CONF. Snap creates a header for the unwrapped phase, and because I've already run the unwrapping, there's a IMG file. When you first do the export, this IMG file won't exist. And now if you look at the snafu.conf file, at the very top of this snafu.conf file, it gives you the snafu command that you need to run. Because we've taken a good number of looks on this image, it runs very quickly. It takes just a few minutes to run. If you take fewer looks, snafu could take a very long time to run, even hours, and it could use a huge amount of memory. So in general, you want to take as many looks as you as you can to reduce the time in the snafu process. If you were to try to unwrap this whole scene without taking any looks, it would probably take around 80 gigabytes of memory, which obviously, if you're running this on a desktop or a laptop, is going to be a big problem, and maybe even crash. Because I've taken 17 looks in range and 5 looks in azimuth, it's going to take just about 2 minutes to do the snafu unwrapping. And you can see here in the slides, it's gives some explanation on how to do this. And the next step is the phase import. These header files that it creates are in the format of, I think, the Envy software, or I'm not sure. So you might be able to use another program to do the to look at the products once they're created. Snafu is still running over here. Now it first does a initial calculation. It calculated something called the network flow. Now it's trying to improve that. It's almost finished. Yep, 2.5 minutes. This is on an iMac. It's 3 years old. Okay, now we're, as explained in this slide, we're going to need to import it back into Snap. Under Radar Interferometric Unwrapping Snafu Import, you need to, so the way the import works is that you need to get some information from the wrapped image. So the default is to keep the same image that the wrapped image that you exported as the source product. Then under this second tab, you need to get the unwrapped phase. So here's where we need to go and find the unwrapped phase. It's under my demo snafu UNW in this long name directory. Unwrapped phase. You need to select the image, the one that has. You need to select the HDR. Because that'll give the information it needs to get the IMG file. Select. And it's just going to save it here in my process products. So I'm not going to run this again. I'll just save some time. I'm going to go back here, just load the product that I already had saved. Now, if we go to this new image, it has the original wrapped phase. Oh, I guess I didn't do the import on this one. It's this one. Sorry. You'll see the original I and Q of the complex numbers, the coherence, the wrapped phase, and now we have a new band called the unwrapped phase. We display this, it looks very different. Instead of that repeating fringe pattern, we have a new range that goes over a large range. First time I opened this, it had a different color stretch, but I went in here under the color manipulation and pressed the 100% here to have it stretch the color range to the whole range.
of values. Because the earthquake is a very small part of the scene, the default is not very appropriate because it loses the big signal. And we can see the values here go from minus 55 to 39, but these are in, this is still in radians. So you need to take these numbers and divide by 4 pi, multiply by lambda to get the radar in meters. But they have an application to do that. We can go back here under products, phase to displacement. We choose our unwrapped phase here. It doesn't have any processing parameters because it already knows what the radar wavelength is, and it's just going to add DSP to the file name, DSP for displacement. I'm not going to run this. I'm going to go back and get the one that I already saved. Here's our new bands. In this case, it only has one band because it's only converted the phase, and it's now displacement band. It automatically switches to a different color scale. I don't know why, this is kind of an ugly color scale, but that's the one they have as default. Again, when I first opened this, it had a different color range, but I pressed 100% button here under color manipulation to have it do the full 100% range of values. And now we can see that the minimum is 0.17 meters, and the maximum is 0.24 meters, 245 meters. And that's the range of values in the unwrapped phase. One of the other things to notice is that my original interferogram phase, the phase was negative in the area of the earthquake. And that's because I used the earlier image as my reference image, and the interferogram subtracted the later image from the earlier image. That means that things that got closer to the satellite during that time interval have less phase and therefore negative. The phase to displacement calculation changed the phase so that the positive displacement means towards the satellite. So it's now positive in this area because it's moved up and towards the satellite. It's one of the things to always be careful with interferometry is the sign. Make sure that you're interpreting the sign of the motion correctly. It's very easy to get the wrong sign. And then the final step is geocoding it, putting it back into the original coordinates. And that's what the SNAP program calls terrain correction, because it uses the DEM to do the correction for radar relief displacement. And it's range Doppler terrain correction here. This is explained also in the slides. This is the phase unwrapping slide. The default is just to take the one band of the image that you selected. In this case, I've selected just the displacement image. It's going to use the SRTM DEM again. You could change to a different DEM if you need a higher resolution. 3 arc seconds is about 90 meter resolution. My pixel spacing is, it's estimating that the ground spacing is 70 meters on the ground, which is pretty close to the SRTM resolution, so it'll work well. But it's actually going to, you can also choose a different map projection. I'm going to leave it in geographic or lat long. That means it's going to be evenly spaced in latitude and longitude. And in fact, it's going to use a pixel spacing of 6 times 10 to the minus 4 degrees, which is the same as the 70 meters. And you can, so the default is just to output the input source band, but you can also have it output the DEM elevations and other information if you want additional information. So again, I'm just going to go and grab the one that I pre-computed, save some time. It adds an underscore TC to the name. And it's changed the name here to displacement VV because it's the VV polarization. Again, you can go back here under color manipulation and change the scale. This one is the, I can press 100%, have it redo the scale to see the full range. Sometimes there's a display glitches. If you zoom in or zoom out, it'll work better. So now under the slides, this is the final result for your unwrapped geocoded interferogram. The next phase is actual doing some analysis. And so there are some types of analysis we can do right here in the Snap application. One of those things is taking a profile across the interferogram. You can just draw a line using the line tool that's up here at this top bar of the window. Draw a line across the center of the signal. And then go up here under raster analysis profile plot. And here we can see that the phase, the displacement in meters across this line goes from around 0. Probably I need to make that line longer. Let me do that. Yeah. Make a new line. We can see that, well, in this case, it starts a little bit negative and then goes up to around 0.24. If I had done the profile from further away, it would actually be even more negative, and that explains why the full range of values is a little bit less than the. There's no true zero in the interferogram, as I mentioned at the very beginning. So the fact that this is negative doesn't mean anything. The zero, we need to use other information, like the fact that we believe that the deformation goes to 0 at some distance away from the earthquake to determine where the 0 is. So in this particular profile, I might say that the 0 is at minus 0.05. So that means I need to add 0.05 to all these values to get the full earthquake deformation. Depending on where other factors, there may be some atmospheric noise in the scene. You might have more work to figure out where the 0 is. But that's one of the things you need to keep in mind when actually interpreting the interferogram. Let's see what else can do here. I had a slide under analysis, profile. Oh, unwrapping errors. If I zoom in on this, and look here near the coast, we can see that there's this area where the phase goes from the displacement is suddenly drops as it gets closer to the coast. If we go back to the wrapped phase, we can see the same area. If you just sort of look at this, you can see that the fringes probably are continuous because they're smoothly going through this area. But there's a zone here with a low coherence or a lot of noise. And apparently that caused a problem when the phase unwrapping, and it got a different answer for the fringes on the coast side of this noisy area than it did on the other side. So that's why our displacement here has this funny jump in it, and that's what we call a phase unwrapping error. It did the phase unwrapping, but it made a mistake when it went through that noisy area. So that's something to keep in mind when you're trying to do further analysis, is to look for these phase unwrapping errors. It takes quite a bit of time to realize, look at a lot of these and figure out what. But when you see these sharp jumps in the phase, and you know that the earthquake signal is supposed to be smooth, then you can be really suspicious that it's probably a phase unwrapping error. I could go back and change the filtering, or take maybe more looks or fewer looks and see if we can get a better version of the phase unwrapping. But those are some of the things that you can try to get a better phase unwrapping. Next slide. For further analysis, you really need to export the data to another program. So in Snap, we can go back here and just Snap and do Snap file export. And if you can export the image as a GeoTIFF, I'm going to take this terrain corrected displacement image and write it out as a GeoTIFF. I'm going to put it in the demo directory. I already have this, so I'm just going to do it again. GeoTIFF is a good format that we can use to load into other software. I'm going to use public domain, free and open software called QGIS. This will be able to open that GeoTIFF image. I'm going to make a new project just to show you. It's a raster image, and I'll find that the GeoTIFF image that I just saved, and here it is loaded into QGIS. You could do similar display in ArcGIS, the commercial software. QGIS, we can go in here and change the colors to be pseudo color. Take the default here for the range. What happened there? Oh, I didn't press classify. Actually, I prefer for the interferograms to use a blue to red color scale. And just invert that and change the positive part to go up to 0.25. And here's the interferogram in QGIS. I have a previous project saved here on my QGIS, which I've done. So I've loaded that interferogram along with some other data. Like one of the things you can get is the polygons that show where land and water is. That's this blue for water. And then I've also gotten these magenta lines here, which are the contours of the depth of the subduction zone. You know, this particular earthquake was in the subducting slab underneath southern Mexico, so this tells me the depth of the earthquake. I also plotted some locations for the earthquake. The magenta square here is the first location that was done by the USGS, National Earthquake Information Center, NEIC. And it's actually, you can see very far away from the signal that's shown up on the interferogram. The green star is the location done by the Mexican Seismic Network, SSN, Servicio Sismológico Nacional, and it's much closer to the earthquake signal. So because they use local seismic stations, they're able to get a much more accurate location for the earthquake. One of the other things we can do once it's in ArcGIS is load other things. For instance, I made this map here in QGIS. It's the same things, but adding a latitude, longitude grid and a scale bar, and actually projecting it into UTM projection. So you can do a lot of things once you have it in a GIS like this, or put it into something like GMT, the generic mapping tools. To do more complete analysis, one of the things that we can, by looking at this view, we can see that the earthquake deformation is actually very close to the center of to the edge of this subswath. So we really need to get the other subswath here before we can do a full analysis of this, to be sure that we have the whole deformation of this earthquake. So one of the next things to think about is merging subswaths. There is a snap tool called the merge tool. One of the other things in snap that I use is this INSAR graph, load graph. It's a whole workflow of a bunch of steps together that you can run, and this shows how the steps are done. So you need to do these same steps in these order. There's that co-registration step that does the splitting and the back geocoding. You need to run that on the 3 different subswaths. And the 2 scenes form pairs for each one of the subswaths. Do the interferogram, do the deburst step, and then finally you can do the merge step. It's kind of a lot of extra work, so that's why they have the system set up where you can load that graph and then set up the inputs from the scenes and then have it go through all these steps. It can use a lot of memory, so you have to be careful not whether your machine is capable of doing that, all those steps. So that's another thing you can that I mentioned at the very beginning was this getting ready for NISAR. Back at one of the products that showed up when I did a search there at the Alaska Satellite Facility is a getting ready for NISAR product. It's this beta interferogram product that I mentioned earlier. It was processed by the ARIA project at JPL and then stored at the ASF archive. This is just to get an idea of what kind of interferograms people might be getting from the NISAR mission in the future. But in this case, it's a useful thing to look at because it has all three of the sub-swaths stitched together and 2 slices along track. And we can just download this interferogram and coherence file map. It's 280 megabytes, but it's the whole image already processed into an unwrapped interferogram. And that product can then be loaded also into QGIS. This is the that interferogram with all the. Now we can see that there's the full width, 3 subswaths. You can see these jogs here to the edge of the subswaths, and it's much longer along track. It's got 2 of the slices or frames, and this is now the full earthquake signal for sure. Probably in this case we didn't really need to do the along track ones, but it's already there. So in this case, I have a different 0. So the peak here is going up to 0.4 meters, just because of that shift, of the arbitrary shift of the phase. And the next thing I wanted to talk about, the last thing I wanted to talk about is a little bit about the earthquake analysis. I've done some modeling on this earthquake. This is a very large topic. I'm only just going to give a quick introduction. We can use one or more of these interferograms to estimate the slip on the fault at depth. The first step is to take the data, that interferogram, and cut it up into do some samples to get a smaller number of samples. I've used a specific program that puts more samples where they are more important. So each one of these squares is a sample from the interferogram. I went through an inversion process to figure out what parts of the fault slipped at depth. And then I created what I call a synthetic interferogram. This is taking the fault slip and then back calculating what the surface displacement is. And this is the synthetic interferogram. And now in the synthetic interferogram, we can see more clearly that there's actually an area of negative displacement here. Typically in earthquakes, you have both positive and negative earthquake displacements. But in the original interferogram, that negative displacement was kind of hidden in this sort of blobby atmospheric noise. So it wasn't very obvious. But it was actually present in the original interferogram. And down here at the bottom, we have the residuals, or the difference between the synthetic interferogram and the real interferogram. And this is basically all the atmospheric noise that was in the original interferogram. If we saw some pattern that was here in the area of the earthquake, we might indicate that we weren't fitting that our fault model wasn't very good. But in this case, because the noise looks the same throughout the scene, we think we have a good earthquake fit. And then this is just a map view of the slip on the fault. I used a special kind of inversion. It's called Altar. I don't have time to go into that, but it's showing that the slip at depth is actually very concentrated, and it's actually a little bit further inland than the main INSAR signal. We saw this area of uplift, but the earthquake slip is actually in the area between the uplift and the subsidence part of the signal. The yellow star is that Mexican earthquake SSN location, and the big red star is the USGS location, and these are some other locations. So we can see that these revised earthquake locations are much closer to the actual earthquake slip than the original USGS location. And that's a known thing, that when the USGS locates earthquakes in Mexico, with only the global network, they can have errors of up to 30, 40 kilometers in the earthquake location. We think that's because of the distribution of velocities in the earth beneath Mexico. The other networks, the other locations that use data from the local network get a much better location. And for this particular slip model, I used 3 of the Sentinel interferograms, the ascending track one that we have been looking at, and then 2 other interferograms from descending tracks. I also used data from the ALOS-2 satellite and some GPS data. So in general, it's always much better to have ascending and descending interferograms to get a better idea of your earthquake slip. And so that's a more advanced part of the analysis that we have to learn in another class. And so the bottom line is there's a lot of information in these interferograms about the earthquake. In this case, we could see that the earthquake location was some distance away from where the USGS location initially. This is the location that they did within a few minutes of the earthquake before they were able to get data from the local networks. In fact, I sent them this interferogram as soon as we were able to get the data, so they were able to use that to help revise their earthquake location. The Mexican seismic network was able to get a location much closer to the actual earthquake slip because they had the data from the local networks. So that's the bottom line. I think it's a lot of steps here, but we can learn a lot about earthquakes from the SAR Interferometry using Sentinel data and in a few years from data from the NISAR mission or other satellite missions. So I think now I can have a time for questions. Hello, this is Eric Fielding again. Ready to answer questions. We have questions here. Okay, so can 2 satellites with the same specifications be used for repeat pass interferometry? Yes, what the Sentinel-1 and 1A and 1B is a clear case of using 2 different satellites that are designed to be compatible. Another case is ERS-1 and ERS-2 that were built to be compatible back in the 1990s and early 2000s. Can interferometry be used for erosion mapping? You can do interferometry to measure erosion by making the DEMs. And that's best done with the single pass interferometry, where you have two antennas acquiring two images at the same time. Not by doing repeat pass interferometry, because the repeat pass interferometry will have lots of errors that are due to changes between the two times that the radar images are required. What kind of technology is used on the Mars missions? So far, the missions sent to Mars are using what they call sounding radars, which are very long radar wavelengths, as much as a kilometer. Those very long wavelengths are not affected by the very thin Mars atmosphere. Processing persistent scatter interferometry. One of the main packages available as free and open source is called STAMPS, S-T-A-M-P-S. That's the SNAP software can be used to prepare data for stamps. How can we use INSAR in the domain of meteorology? This is an interesting question. We had a workshop about this a few months ago, where we had meteorologists and INSAR people working together to talk about this. Because the radar signal is very sensitive to water vapor in the atmosphere, when we make interferograms, that we can actually get a snapshot of what the water vapor is over a given area at the time that the satellites went over. Because we're doing this repeat pass interferometry, it's always a mixture of the atmosphere on the first date and the atmosphere on the second date. One of those is positive, the other one's negative, so it takes some effort to try to determine which date had the water vapor variation, but it is possible to some extent. Aside from ALOS, TerraSAR-X, TandemX, and Sentinel-1, all of the missions that I mentioned on that chart can be used and have been used for making interferometry. ERS-1 and ERS-2 and NVSAT have been used for many, many years to do interferometry. And the ERS-1, ERS-2 have the longest time series available. But all of those can be used for interferometry. Not all of the data is easy to get. Some of it's more commercial. How can we decide which subswath to select for co-registration? Well, you have to look at the overview image and see which one of the three subswaths covers the area that you think the earthquake is in. In this particular case, I looked at the location from the USGS and the Mexican network, and determined that subswath 1 that I showed in the demonstration was the one that covered the earthquake. Other cases, it might be on the boundary, and you may have to process more than one subswath to see the full earthquake signal. For multi-look parameters, what's the guide to get the number of multi-looks? In general, for most earthquakes, taking 17 range looks is a good number. That gives you a ground range spacing of around 70 meters. That's good for most earthquakes, unless you really need higher resolution. And the SNAP program automatically estimates how many azimuth looks are necessary to get roughly square pixels on the ground. So once you choose the range looks, it determines the azimuth looks. How does the number of tile rows and columns affect the phase unwrapping process? The SNAFU program has an option for processing the data in multiple tiles to break down the problem into smaller pieces. This is necessary if you're taking a small number of looks, because then each tile will be small enough to run on your computer. But it can lead to errors if it's not able to determine the relative phase between the different tiles. So in general, it's better to set the number of tiles to 1 if you can, and only use more tiles if it's necessary to make it run on your computer. You don't have to. You can change that in the snafu configuration file. You don't have to redo the export. Is erosion mapping in volume not possible, since vegetation mapping is volumetric and it becomes dirt? Yes, the problem, once you change the ground surface, if it's any kind of erosion, it changes the ground surface. That means that if you do a repeat pass interferometry, the surface will become incoherent. So you can detect where there is erosion by looking at the coherence, because suddenly the coherence will go to essentially 0. The correlation or coherence will drop if there's been a significant erosion, but you can't measure the volume of erosion with repeat pass interferometry, because once it's incoherent, there's no phase measurement. It's just noise. The only way to do volume mapping is to use the single pass interferometry, like the GLISSEN system, the airborne NASA airplane, or Tandem-X, the German system, where they are operating the 2 satellites in the bistatic mode, where the 2 satellites are turned on at the same time. That's the only way to measure volumes of materials once the landslide or other process has moved enough to be incoherent. What we can measure for landslides is landslides that are moving slowly. So if they've moved only a few centimeters, or maybe tens of centimeters, then in some cases you can still they move as a block and slide coherently. Then you're able to make the interferometric measurement with the repeat pass interferometry and see how far it's moved. I did with the airborne system, we were able to get the 4 different look directions in order to determine the full 3-dimensional motion of the surface, whether the horizontal motion and the vertical motion. With the satellite systems, we're able to measure, in general, only 2 components of motion, the vertical component and the east-west component. All the existing satellites are in polar orbits, and so they don't have much sensitivity to any north-south motion, and we can't determine the full 3-dimensional surface motion. And the other advantage of the airborne SAR is that it's higher resolution. The satellites are generally much lower resolution than the airborne systems. Sentinel-1, the radar, you really can't see anything that's not at least 200 or 300 meters across. And that rules out measuring landslides that are relatively small. We use this airborne system, UAV SAR, to measure landslides that are as small as just 100 meters across, or even 50 meters across. Question 12. From a disaster recovery and monitoring standpoint, can you model the reconstruction of neighborhoods? We can, with this damage proxy map or coherence change technique, we can measure when the ground or the buildings have changed. So in fact, we can see where buildings are being built in addition to buildings that are being removed. That's or if you have the single pass interferometry where you're getting the elevation, you could actually see the change in elevation of buildings. But if it's if you're just looking at the coherence change with repeat pass interferometry, then you can't determine what has changed. You can only say that something changed within this area of these pixels, and you can't say whether it was a building being built or a building being torn down or exactly what happened there. In fact, in one case, after that earthquake in Iran, there was an area that had low coherence after the earthquake, and it turned out that that was an area where they had built tents to put the survivors as temporary shelter. So we could see that part of the recovery process where people had put some temporary shelters. If you have enough imagery, could you create a DEM with a higher resolution? I don't think anybody's ever done that. It's the interferogram process. To make DEMs, we always do some amount of multi-looking. So the DEM always has a coarser resolution than the original radar data. For TerraSAR-X, the TerraSAR-X TandemX DEMs, their raw data resolution is around 3 meters, but they choose to make DEMs at a ground spacing of 12 meters because they need to take some number of looks to be able to get the noise level to the point where it's accurate enough to make a good DEM and to do the phase unwrapping. Phase unwrapping is necessary to make DEMs just as it is for making displacement maps. So I don't think there's any way to make higher resolution DEMs than the resolution of the radar data that you have. Question 14, how would you know if you have noise in your data? The thermal noise removal. I'm not sure what the thermal noise removal does in SNAP. I think that's more for the amplitude, the radar amplitude, backscatter amplitude, and I don't think that's going to help with interferometry. For interferometry, you need to use those interferometric filters, like the Goldstein filter. I don't think that I don't know what the thermal noise removal tool does, but I'm pretty sure that's not going to work for helping with the phase. Can you mix different types of same band satellites? If the satellite is in a different orbit, then it's not possible to use data from different satellites, even if they're in the same radar wavelength. It turns out that they launched the NVSat satellite. The ESA launched the NVSat satellite in the same orbit as ERS-1 and ERS-2. So there are some cases where you can make interferograms between the NVSat satellite and the ERS satellite, ERS-2 satellite, but they actually changed the radar wavelength slightly between ERS-2 and NVSat, and that means that only in very specific conditions of a very long baseline will the length of the baseline cancel out that difference in the radar wavelength and give you a coherent image. It's kind of, in general, the different satellites are in different orbits, and that means that they're not even close to the same position, so it's impossible to do any interferometry. You can combine data from different satellites in the final modeling steps. Once everything's been converted to displacement in the radar line of sight, then the earthquake modeling tools can combine data from different satellites into a more complete picture of where the faults moved, or landslides or something else. Question 16. Can interferometry also detect water level changes? There are certain cases where repeat pass interferometry stays coherent in areas of flooded vegetation. That's like swamp, wetlands areas. I know a colleague of mine in Florida looked at water level changes in the wetlands of Florida. And because of the presence of the vegetation, the radar backscatter stays relatively stable because of the vegetation. And if the water is not, there's no waves on the water, it's very calm water, then it can stay coherent. And when the water level changes, it changes the phase due to the double bounce having a different distance. And in that particular case, it is possible to estimate water level changes. In general, if it's open water, like a lake that doesn't have any vegetation in it, that has wind and waves, then the water surface will change too much between one image and the next, and you'll have zero coherence, and you can't measure anything. Only with the single pass interferometry can you measure water levels everywhere. And in fact, there's another mission being built by NASA at JPL. It's called the Surface Water and Ocean Topography Mission, and it will be using SAR Interferometry using two antennas on the satellite to measure water elevation both over the oceans and rivers and lakes. So there's actually another, that's the SWOT, SWOT, SWOT mission. So that's that will be measuring water level changes with interferometry, but it's single pass interferometry, not repeat pass interferometry. So question 18, is the SAR-derived displacement added to the DEM? You could do that, yes. I think people have done that in a few cases. I can't think of a specific example where somebody's done that. If you have very large displacements, you might be able to even do differencing between two single pass interferometry DEMs and see the elevation change if it's many meters. But you certainly in the case of this earthquake in Mexico that we used in the demonstration, it moved the ground surface upward by 40 centimeters, or 35 to 40 centimeters. So that should be added to the elevation, at least during that time interval. Subduction zones, the ground is going up and down over hundreds of years as the different parts of the subduction zone slip. So in fact, that's one way that we know about very large previous earthquakes, is seeing the vertical motions that were recorded in the past. So you could make a new DEM if you want. Usually the earthquake deformation is a very small percentage of the actual elevation. Question number 19. Yes, is the earthquake displacement along the radar line of sight? So yes, that is something that I think I mentioned at one point, but didn't go into detail. I should have explained that more completely. The interferogram, repeat pass interferogram, is always measuring the displacement in the line of sight between the ground surface and the satellite. And that means that you're only getting one component of the earthquake displacement. There is a special kind of a different type of interferometry that we called multiple aperture interferometry. That's really an advanced technique that can measure displacement in the along track direction. That would then allow you to get both horizontal and vertical components, but it still only gives you two components of motion, where you always need at least two different satellites to get the full three-component deformation field. So that's and the other way to get to separate the horizontal and vertical is to just combine data from different satellites. Especially the ones ascending and descending. Ascending is when the satellite is going north and usually looking east, and the descending tracks where the satellite is going south and looking to the west. And by combining those two different look directions, then you can separate the vertical motion from the horizontal motion in the east-west direction. You need to use that special multiple aperture interferometry to get anything about the north-south direction. And that multiple aperture interferometry with the present satellites also, the north component is always much less accurate than the east, west, and vertical components. Question number 40. Can phase unwrapping errors be induced by a poor quality reference DEM? Yes, if you have if your reference DEM has errors in it, and you subtract out the topographic phase based on that DEM, then it can certainly introduce phase artifacts in your differential interferogram, and that could cause phase unwrapping errors and other just straight errors in your final displacement map. What is the minimum number of INSAR images required by the PS, or persistent scatterer approach? Most of the persistent scatterer approaches require on the order of 20 INSAR images over the same area in the same track. I think some can work with maybe a little bit less than 20, but usually the 20 is kind of the minimum number, and people prefer to have 50 or even 100 images to really get very good quality persistent scatterer analysis. Number 22. It was found that there was extensive rainfall due to Hurricane Harvey in August of 2017 caused land deformation. Yes, the weight of the rain, all that water on the land pushed the land downward. One of my colleagues right across the hall here has done a lot of research on that. He used measurements from the GPS stations in the Houston area, and I think he has a paper that's going to be out very soon on that. That deformation is over a large spatial scale, and it's in an area that has a lot of vegetation. We looked at the SAR Interferometry data to see if we could see that deformation. It was hidden by the decorrelation due to the flooding itself and the vegetation there in Texas, and also by the water vapor in the atmosphere. It's a few centimeters of deformation over a large area is very similar to the type of signals that we see, the type of noise that we get from water vapor in the atmosphere. So that particular type of deformation is difficult to measure with SAR interferometry. If it had stayed there for a long time, then we might have had a chance to measure it, because then we could take multiple images and avoid the noise from the atmosphere. But because it was over a short period of time and a large spatial scale, then it's hard to measure that type of deformation with SAR interferometry. The thing about earthquakes is that the deformation is permanent. The earthquake pushes the land up or down or east or west, and it stays there. So then if the atmosphere is bad on the first image that comes over the area, then you can maybe wait for the next image or the image after that and be able to measure the deformation due to the earthquake or due to, say, groundwater withdrawal by combining multiple interferograms to reduce the effects of the atmospheric noise. And I think that's it for the questions. And thank you all for listening in. It's been a long webinar, and good night to everybody. Thank you.